says there's a connection. Do I need to click a button on YouTube that says go live every single time I try to do something? Oh, this is an enormous pain in my butt. All right, well, I think I fixed it. Don't love it. Don't love the thing that has changed, that was working and now is no longer working. But okay, yes, everybody can see. Fantastic. We've fixed the problem that wasn't previously a problem. Paper reading group. Sorry for that very gummy introduction. So we're starting a new paper. And the paper was published in Tackle, which is the Transactions for the Association of Computational Linguistics. And I mentioned a couple of times that sort of the fanciest place to publish papers in linguistics or in NLP, sorry, are these conferences run by the ACL, the Association of Computational, which is just a scholarly organization for folks. And sorry, my mic is not in the right position. There we go. Those are better levels. Big mess this morning. So Tackle is the journal for that paper, for that organization. And then the papers that are accepted into the journal are presented at one of the STAR ACL conferences, one of the conferences run by ACL. And this is one of them. So I don't know what conference this was at, but it is in the journal, if that makes sense. Tackle papers are a little bit, have more moving parts than regular conference papers, and they are also usually a little bit longer. So this paper has a lot of authors, and I am not going to read all of the authors, but here they are. And the top three are Jacob, Andreas, John Bufe, maybe, David Burkett, and Charles Chen, and then additional authors. And I believe that most of these authors are out of Microsoft is the word that I was going to say there. I want to say, like, so there was a dialogue systems related company that was acquired by Microsoft, and I think a lot of these folks are from there. And I want to say it's called Semantic Systems, but I don't quote me on that. And does it have their affiliation? Semantic Machines, sorry. So I believe that Semantic Machines was acquired by Microsoft, and then this is a paper by that team. And I think they're in research, but I could be wrong. I'm excited for today's session. Oh, thank you. So, let's get started. The title of the paper is Task-Oriented Dialogue as Data Flow Synthesis. We describe an approach to task-oriented dialogue in which dialogue state is represented as a data flow graph. A dialogue agent maps each user utterance to a program that extends this graph. Programs include metacomputation operators for reference and revision that reuse data flow fragments from previous turns. Our graph-based state enables the expression and manipulation of complex user intents and explicit metacomputation, which makes these intents easier for learned models to predict. We introduce a new data set. Ooh, new data set. Flow. SMCalFlow, maybe. Ouch. Featuring complex dialogues about events, weather, places, and people. Experiments show that data flow graphs and metacomputation substantially improve representability and predictability in these natural dialogues. Additional experiments on the multi-WAS dataset, which we've talked about in other papers before, show that our data flow representation enables an otherwise off-the-shelf sequence-to-sequence model to match the best existing task-specific state tracking model. The SMCalFlow dataset, code for replicating experiments, and public leaderboard are available at Microsoft website. Let's go through that one more time, because that was a lot of words. So task-oriented dialogue is your I like to think this is sort of like the majority of dialogue systems that get built. This is sort of in contrast to chit-chat systems where the goal is just like, I want to talk to a computer, and task-oriented is like, I need to order a pizza, or I need to update my checking account number, or whatever. In which dialogue state is represented as a data flow graph. So I'm not super familiar with data flow graphs. I'm guessing based on sort of their discussion here that it's going to be some sort of directed graph structure. I don't think it necessarily needs to be acyclic. So if you're familiar with DAGs or directed acyclic graphs, they're a very common data structure, particularly for epidemiology and causal modeling. They show up in a lot of places, but I don't think that it needs to be acyclic, because you can imagine a conversation where you loop back to an earlier part of the conversation. A dialogue agent maps each user utterance to a program that extends this graph. The dialogue agent is just like your assistant. Each user utterance to a program that extends this graph. So they're building a graph over time through reinforcement learning, I guess? I don't know. We're going to learn about it. Programs include metacomputation operators for reference and revision that reuse data flow fragments from previous turns. Metacomputation operators. So metacomputation would be computation about computation. Operators. This sounds like a technical term that I'm just not familiar with. Old Player says something in Russian. From context clues, I'm going to say that's Privyet. Hi. Our graph-based state enables the expression and manipulation of complex user intents, and explicit metacomputation makes these intents easier for learned models to predict. So this is going to be a state machine, which is sort of the more traditional way of doing dialogue systems. And not really what we do at Rasa. We use we use a large number of different dialogue policies, and it's open source, so you're free to add your own. But these days, mostly we're using transformer-based dialogue policies. So it's I'm trying to think of a quick way to talk about the difference there. So instead of like an explicit set of states and directions for going between states, you look at all of the possible things that your assistant can do, and you pick the one that is likely to be the best thing to do next. So you don't have to maintain this graph structure. And what they're doing here is basically, based on this abstract, the graph structure is building itself. So instead of you sitting down and, writing a big old tree for all the ways that you think the conversation can go, Old Player says, I'm not from Russia, I'm from the Ukraine. They're different countries. Yes, I cannot tell the difference between Russian and Ukrainian. So Ukrainian. Again, I'm guessing it's something like hi from context clues. My apologies. I don't read Cyrillic. So I'm guessing what they're going to say, so they have the data set, which is one contribution, and then they have, it looks like it's going to be a system demonstration where they demonstrate that this approach can improve existing commercial systems using the general approach of, have you ever seen that, like, I would, again, just from the abstract, have you ever seen that, like, old clip, I want to say it's Charlie Chaplin, of him, like, on the cattle guard of a train, and he's, like, building track in front of the train as it goes? I don't know that the sort of like learning is going to happen during conversations, but it sounds sort of similar, that you're sort of like extending the next steps based on the current step. So greetings to you as well. Thank you for joining. All right, introduction. Two central design decisions in modern conversational AI systems are the choice of state and action representations, which determine the scope of possible user requests and agent behaviors. Dialogue systems with fixed symbolic state representations, like slot-filling systems, are easy to train but hard to extend. Cracchini et al., 1992. Deep continuous state representations are flexible enough to represent arbitrary properties of the dialogue history, but so unconstrained that training a neural dialogue policy end-to-end fails to learn appropriate latent states. Okay, so what they're saying here is that you have these sort of two ways of doing things. You have, the deep learning approach. This is a 2016 paper, so they're probably not using transformers because those came out in 2017. It's sort of like, probably some sort of sequence-to-sequence model, like probably bidirectional LSTM with attention, given that date. I have not read this paper. I am guessing using my knowledge of the field. And then these sort of more traditional, older types of models, which are, state machines. And state machines, difficult to change once they are up. And these deep continuous representations and the failure to learn appropriate latent states. I don't know what a latent state would be. I'm guessing it's like sort of like a mid point of the conversation. Ooh. Oh, you know what I bet it is? I bet this is talking about complete end-to-end systems where it's text in, text out, and they're suggesting that there's no sort of like modeling of intent or like what the user wants to do in this case. That would be my guess. The paper introduces a new framework for dialogue modeling that aims to combine the strengths of both approaches. Structured enough to enable efficient learning, yes, flexible enough to support open-ended compositional user goals that involve multiple tasks and domains. Compositional user goals, this would be like, I want to do multiple things or things that have multiple parts in them. The framework has two components: a new state representation in which dialogue states are represented as data flow graphs, and a new agent architecture in which dialogue agents predict compositional programs to extend these graphs. Over the course of a dialogue, a growing data flow graph serves as a record of common ground, an executable description of the entities that were mentioned and the actions and computations that produced them. Okay, so this is very similar to, okay, so if you've used Rasa, we have something called the tracker store, which is just like the history of the conversation. And it looks like the difference here is that they have like the tracker store plus in that history, all of the computational steps that were taken to arrive at each point in the tracker store. Or I'm calling it tracker because that's just what we call it in Rasa, but it sounds like it's a fairly different implementation. All right. Interesting. So this is sort of yeah, so a lot of the dialogue system papers that are out these days are more neural end-to-end models, and it sounds like this is a pretty distinct way of thinking about dialogue systems. Okay. Figure 1, a dialogue and its data flow graph. Turn 1 is an ordinary case of semantic parsing. The agent predicts a compositional query that encodes the user's question. Evaluating this program produces an initial graph fragment. In turn 2, that is used to refer to a salient event. The agent resolves it to an event retrieved in 1, then uses it in a subsequent computation. Turn 3 repairs an exception via a program that makes a modified copy of a graph fragment. So let's zoom in a little bit here. Okay, where is my meeting at 2 this afternoon? So the semantic parsing is just sort of, parsing is taking natural text and representing it in a structured format. And then semantic means that you're including the meaning in that structured format. This sort of like parse is like, hey, I need a place, for a specific event, and the event starts at 2. So that's sort of the structure of the meaning there. And the agent sort of follows that and is like, oh, it's in conference room D. Can you create a meeting with Megan right before that starts? So here they're doing a little co-reference resolution. So that is referring to this meeting and figuring that out. Okay, so I see they have this sort of this model here where they're like, okay, 2 p.m. and then that's the start time for this event, and they need to find this event. And then previously they looked at the place, and now the agent's like, okay, instead we're going to look at the start of that, and then we're going to create an event from that, except there's been an error here, and the error is that it's not clear which Megan they mean. So the person needs to then specify Megan Brown. So this is presumably doing some sort of so there's presumably some sort of data storage in the background here with the events on the calendar, maybe a contact list of different people this or colleagues this person can contact. So they want to contact Megan. Specifically, it's Megan Bowen. So this data structure has been revised so that instead of just Megan, it's Megan Bowen, and then they create an event. And the agent says, okay, I'll book a meeting with Megan Bowen from 1:30 to 2 p.m. today. So all of those actions are represented by, all of the things that the agent can do are represented by this sort of graph structure that has this information in it. Yeah, and it's definitely, so it's directed. So you can see that you go from, nodes along these edges, and then the edges go from one direction to the other. They don't go both directions. I realize that sounds like a dumb thing to say, but it is in fact very relevant when you're talking about graphs. And it looks like these are, so the edges are, so here it's that this is the start time for an event. Here it's that this is the name of a person and the attribute of the event. I'm not entirely sure why some things are going on edges and some things are going in nodes, but presumably they'll talk about it. Hi, Faisa. Interesting. Okay. So this is sort of the general idea of how it's working. And then the graph that we were just looking at serves as sort of this record of what happened. Maybe the edges are like lookup events. While this paper mostly focuses on representational questions, learning is a central motivation for our approach. Learning to interpret natural language requests is simpler when they are understood to specify graph building operations. It might be simpler computationally. I don't necessarily think that that's going to be simpler always. So for example, if you were using a graph-based representation for something that it's not, I mean, there's like the second part of it, which is that you need to be able to determine that something is a request. And I guess in this sort of system, these task-oriented dialogue systems, you have sort of the easy thing in that everything that the user says to the system is going to be considered a request. But if I'm just like, ooh, it's cold in here, and I mean for you to close the window or like turn on the heat or something, it's not necessarily clear from a conversation, some of which turns are requests and some of which are not, that that's going to be the case. And in that case, I don't know that a graph is going to be the simplest way to constrain that information or represent that information. Does that make sense? Yeah. Anyway, what I'm just saying here is that this is a pretty strong claim, and instead of is, I would probably say can be. Which, again, I realize that's very nitpicky, but that's what scholarly training is all about, is how to be concise with your language. Human speakers avoid repeating themselves in conversation by using anaphora, ellipsis, and bridging to build on shared context. So anaphora is using a word to refer to something else. So like that, he, she pronouns are a good example of anaphora. Ellipsis is just omitting part of something. So if there are like 4 cups in a room, and 3 of them are within arm's reach of me, and 1 is on the other side of the room. When I turn to somebody, it's like, hey, can you pass me that cup? It is clear from context that I mean the cup that I cannot reach myself, even though I didn't specify that. It's not a great example of ellipsis, but yeah, it does rely on the shared context. Our framework treats these constructions by translating them into explicit metacomputation operations for reference and revision, which directly retrieve fragments of the data flow graph that represents the shared dialogue state. This approach borrows from corresponding ideas in the literature on program transformation, Visser 2001. Gotcha. Okay, thus the metacomputation angle. Got it. And results in compact, predictable program whose structure closely mirrors user utterance. Okay, so this sounds similar to meta-programming research a little bit, and based on their sort of talk on program transformation, it sounds like it might be quite similar actually, which is the idea where you have a program that builds programs, or a computer that builds computational structures for a specific task guided by some goal. Faisa says, now I want to know an implementation for booking a meeting with a Rasa chatbot. Yeah, you need integration to some of the relevant data sets like calendar, but I bet somebody already has one of those that they might have open sourced. So I'd poke around on GitHub and see if you can find one. Okay. Yeah, so I am not super familiar with the metacomputation literature. I sort of know about it vaguely, so I'm hoping they go into a lot more detail. And I think that's also fair for a tackle audience, because we don't, the ACL tends to be a lot of people from very different fields. So some people from speech processing and electrical engineering, although it's not the main venue for speech stuff. People from linguistics, people from computer science. So I'm hoping that we get more information on the background of metacomputation and what they're doing. And then also I think reference and revision are going to be specific things. Experiments show that our rich dialogue state representation makes it possible to build better dialogue agents for challenging tasks. First, we released a newly collected data set of around 40K natural dialogues, okay, not bad, in English, about calendars, locations, people, and weather. The largest goal-oriented dialogue data set to date. Yeah, that's pretty big. How big is the Ubuntu dialogue corpus? I thought it was bigger than that, but I could be wrong. Is this conversation? No, okay, that's dialogues. Ubuntu dialogue corpus. How big is it? Size of the blobs, not what I'm looking for. I'm just gonna pull this up really quick. This is just a mirror of the corpus on Kaggle that I uploaded. 930,000 dialogues. Okay, well, I guess it's sort of arguable about whether or not the Ubuntu corpus is task oriented, because it's people asking for help in listserv. I don't know. Each dialogue turn is annotated with a program implementing the user request. Many turns involve more challenging predictions than traditional slot filling, with compositional actions, cross-domain interaction, complex anaphora, and exception handling, figure 2. On this dataset, explicit reference mechanisms reduce the error rate of sequence-to-sequence with copying models, see et al. 2017, by 5.9% on all turns and 10.9% on turns with a cross-turn reference. To demonstrate breadth of applicability, we additionally describe how to automatically convert the simpler multi-WAS dataset into a data flow representation. This representation again enables a basic sequence-to-sequence model to outperform state-of-the-art task-specific models at traditional state tracking. Okay. Oh, I see, I see. So they're saying that you can use this representation with sequence-to-sequence models and it will be like part of the sequence. Gotcha. Okay, so then they probably are acyclic, the graphs. And that you can use this additional representation as sort of like an extra layer in your model and get really good results. That's the argument. Our results show that within the Dataflow framework, a broad range of agent behaviors are both representable and learnable, and that explicit abstractions for reference and revision are the keys to effective modeling. Okay, so they're saying that you can model different agent behaviors in this sort of like very clear, unambiguous format, and that you can learn those representations. You don't have to create them by hand for every turn. All right. Andreas says, I just started off with Rasa and I'm loving it. Oh, I'm glad to hear that. I'm new to this area of machine learning, NLU, and AI. How can I increase my knowledge in this area? Great question. If you're interested in just sort of general, oh, you didn't say, if you're interested in just sort of general NLP, I'd recommend the Speech and Language Processing textbook by Dandrafsky and last name Martin, first name Dean. It's not Dean Martin. Drafsky and Martin, which is available for free online as sort of the usual textbook. We also have the Rasa Masterclass, which walks you through the process of building an assistant with Rasa, and also has like sort of more in-depth explanation of like how things work. And that's also available as an ebook for free. So, hi Marco. And how near this says, yep, that makes sense. Good. Yeah, interesting. So this feels pretty, so there's this tradition out of Berkeley about a way of representing meaning as sort of like a series of nested data structures that are connected to each other, and this feels vaguely similar. And that's what I have to say there. All right, dialogue and data flow. Let's learn more about this data flow structure, because it seems like this is the thing that the whole paper is built around, are these graph representations. Feza says the Rasa community, the docs, the tutorials, the GitHub, and so on. Yeah, we also have a forum that's linked in the video description. This section provides a high-level overview of our dialogue modeling framework, introducing the main components of the approach. Sections 3 to 5 refine this picture, describing the implementation and use of specific metacomputation operators. Great, so they're going to talk about those. These are things that are like revise and reflect. I don't remember the two operators they talked about. I don't know what they do. I could sort of guess based on the names, but I don't know that I'm going to be right. We model a dialogue between a human user and an automated agent as an interactive programming task where the human and computer communicate using natural language. Dialogue state is represented with a data flow graph. At each turn, the agent's goal is to translate the most recent user utterance into a program, so map it onto a graph and then decide what to do. Predicted programs non-destructively extend the data flow graph, construct any newly requested values or real-world side effects, and finally describe the results to the user. So we're adding to the graph. We're making it bigger. We don't erase any part of it. Construct any newly requested values or real world side effects. So I'm guessing that would be like updating the underlying data set, that like, oh, you're scheduled now, I'm going to mark that in your calendar, I'm guessing, or like do the thing where you send a calendar invite to somebody else, and then describe the results to the user. So like, our approach is significantly different from a conventional dialogue system pipeline, which has separate modules for language understanding, dialogue state tracking, and dialogue policy execution. And that's sort of how Rasa works. Oh, we got some stream instability. So that's not ideal. Omkar says, is it true that regex are not explicitly tagged with intents and entities? How can we use them to enhance entity extraction? How does Rasa work with the backend using regex? So regex, all right, and we're back. Fantastic. So regular expressions are basically just a way of matching particular texts. So you can use regular expressions to match, you know, text that has specific qualities, and it's just sort of a featureizer. So it's not going to be, so you would put it earlier in your pipeline than your intent classification, if that makes sense. And back. Fantastic. And we could do a whole big thing about regular expressions. I will add that to the list. There might also be some videos already. I don't remember if Vincent has done any, but I think Yusta has. So you might be able to find some videos on the channel already. All right. What were we talking about? They extend the graph. Our approach is significantly different. From the way that we work, which language understanding. So taking the text and then transforming it to a computer readable format. Dialogue state tracking, so what have you done, what are you going to do, that's the tracker system that I mentioned, and then the dialogue policy execution, which is what do you do next. Instead, a single learned model directly predicts executable agent actions and logs them in a graphical dialogue state. Oh, this is very interesting. Marco says, what do you think about extending the short-term memory context of a dialogue? So like using a longer windows for LSTMs, it'll slow down your training a lot. If long-term dependencies are important to you, I would in general recommend transformers. Just because of you can train in parallel. So if you're using hardware acceleration, you can dramatically reduce your training time with transformers. The trade-off with that is that you generally need more weights, but the trade back, I guess, is that there's some pretty effective pruning strategies so that you can reduce the number of total weights while maintaining model performance. That's my answer. Hopefully that was helpful. All right. Programs, graphs, and evaluations. The simplest example of interactive program synthesis is question answering. So the user, when is the next retreat? And then we have this this data structure here, which I'm guessing you actually compute, you read out from, right? So you figure out the current time, and then you need something that starts after that is called a retreat. And that's an event specification, and you use that as a query to find an event, and then you return the start time. And the agent says it's on April 27th at 9 a.m. Here, the agent predicts a program that invokes an API call find event on a structured input event specification, I'm guessing, to produce the desired query. This is a farm of Semantic Parsing, Zell, 1995. Okay, so there are actually different things in here. So this is an API call, and this all is a query that is sent to that API that has a specific structured input. And then from that, we get this start time. Okay. Oh, and I see the, I was like, there's no way to differentiate them. The capitalization is different. I would probably have color coded this if I were doing it in a paper just to make the lives of people like me easier. Here the agent predicts a program that invokes an, okay, so they did this prediction. The predicted program above can be rendered as a data flow graph. Okay, so you do read from the inside out because you're starting with now, after, and then also you have this additional information retreat, and all of that information is needed for this query. So the name doesn't depend on the time. In this particular instance, they are both just sort of inputs to this event specification. and then you run the query, and then you get just part of the query back, which is the start time. Oh, I see. So these the edges are like field names, keys, and then the values go in the nodes. Does that sound right? That sounds right-ish. Okay. Each function call in the program corresponds to a node labeled with that function. Okay, so the nodes are functions. The node's parents correspond to the arguments of the function call. Node's parents, so these ones, the ones above it in the tree structure or that come before it in the execution order, are so that inherits these are the arguments. The top level call that returns the program's result is depicted with a solid border. Hold up. If this is the top level, sorry, that's just a little confusing because I think of parents as being above children, and this is like, maybe this is just like my bias from the like graph reading training that I've had. So it is weird to me to say that's the top level, because then you're going up. So the parents are below the children, which if you're using the family tree metaphor is a little funky. Okay. The final call is depicted with a solid border, but it does make sense because that's what's on the outside of this sort of like nested structure. A Dataflow graph is always acyclic. Okay, so it is acyclic. It's a directed acyclic graph, but is not necessarily a tree, as the nodes may be reused. With the same values? Once nodes are added to a Dataflow graph, they are evaluated in topological order. Evaluating the nodes applies its function to its parents' values. Evaluating a node applies its function to its parents' values. Okay, so I think by topological order here they mean from the beginning of the operation to the end of the operation, but we end at the top. Yeah. Okay. This is weird mixed metaphors, but I'm picking up what they're putting down. Or putting up, I guess. Celia says, can we have a series in the reading group which specifies how the conversational AI journey started and grew to the point it is now? Milestones papers in the domain. Oh, like sort of like a literature review thing where we go through and talk about the major papers. That's not a bad idea. It's a very good idea, but also I have a lot of papers I want to read that are very recent. So if we run into a dry spell, I will definitely keep that in mind. Also, that might be more helpful as like a YouTube series where we just sort of like summarize what's in the papers rather than going through and reading them in depth. Okay. Okay, I'm picking up what they're putting down. And evaluating a node. Here we have annotated two nodes that show the value of after now is a date time spec, and the value of the return start node is a specific date time. Okay, evaluated nodes are shaded in our diagrams. Exceptions, see section 5, block evaluation, leaving downstream nodes. Exceptions block evaluation, leaving downstream nodes unevaluated. Sorry, I garden past myself there. Churik says, I see it more like a TensorFlow graph. Nodes are operations and values are on edges. Yeah, I think that's what they're going for. Yeah, weirdly, most of my graph theory stuff comes from syntax parsing, and then causal modeling, like I mentioned. So my background is a little. I think my background is different than the author's background here. Okay, so this makes sense. The above diagram saves space by summarizing the structured value of a node as a string. In reality, each evaluated node has a dashed result edge that points to the result of evaluating it. So this start goes to date time, which is nodes are operations and values are on edges. Sometimes the value's in a node, though. All right, so you get out this date-time object that has these qualities April 27th, 2020. The result itself is a node in the Dataflow graph. Often a new node is added by evaluation. It may have its own result edge. A node's value is found by transitively following result edges until we arrive at a node whose result is itself. A node's value is followed by transitive. Okay, so if we're going through here, we're following edges, we're following edges, we're following edges. Oh, no edges. Out. So we know that this must be the result because this is where the graph ends at the top. The result is a node's value, blah, blah, blah. Such a terminal node is either a primitive value, e.g. 2020, or a constructor, e.g. date time, whose parent node's values specify its argument. A constructor has the same capitalized name as the type it constructs. Gotcha. Okay, so we're going through, and actually, even though this looks like the final output, it actually has this like hidden additional structure attached to it where we have the date time constructor, which takes in this information and then creates a value from it. So you would expect, so this information should either be something like year or a complete object constructed of, or a complete type, I guess. I don't know. Information? Done information. Okay, and then if you wanted to know the year, you could go here, look at this edge, and then I guess reverse this edge, and then this would be, yeah, no, you have to reverse this edge, because if you just made it bidirectional, then this would have edges coming out of it, and you just bounce back and forth forever. So, like a query here would reverse this edge. Oh, they talked about reversals, didn't they? Yeah, they said that was one of the operations. I'm just really quickly looking to see if we can find where they talk about metacomputation. Metacomputation. Representability, predictability, reference and revision? Oh, no, they didn't actually say reversal. I came up with that. That's nothing. Okay, anyway. Reference and revision. So these are the things that they do, how they change the graph to be able to have additional functionality. We now sketch two metacomputation functions whose evaluation extends the graph in complex ways. As a representation of dialogue state, the Dataflow graph records entities that have been mentioned and the relationships between them. So, with me. As your conversation goes on, your agent continues to construct and extend this graph, which represents the state of the dialogue. All nodes in the Dataflow graph are eligible to be referenced by subsequent utterances. Suppose, for example, that a user continues the previous dialogue fragment with a follow-up question, what day of the week is it? Day of the week, refer, it's a Monday. the user's word that becomes the refer call in our predicted program, as it is a reference to some salient previously mentioned nodes. You're going to have to do some sort of, well, it's not necessarily co-reference, but figure out this thing that was happening before that you're talking about now. Evaluating refer here chooses the top level node start from the previous turn. That node is then used as an argument to a day of the week node. Nodes existing from previous turns are shown here in lighter ink. So here's our structure. We asked for the day of the week. That's added as a function to this. That function is called using the last terminal node as the input, and then we get Monday out as an argument, excuse me. And evaluate the latter node applies the day of the week to its starts value. This diagram is actually a simplification. We will show in section 3 how the refer call itself is also captured in the data flow graph. The user may next ask questions about the upstream constraint of the event's start time. What about in 2021? So this is a revision, and so this is a function and it's doing some stuff. So the new date time uses the existing values, except it adds 2021 as the year, or it updates the year to be 2021. The old location and the root location. I don't know what those mean. Chirag says in the representation A to B is B of A, so the diagram for date time is correct. Yeah. Oh, no, I don't doubt that they're correct. It's just, it's taken me a bit. The new date time specification. Also, I'm guessing that's what spec expands to, but again, I am guessing. Representing in 2021, is to be substituted for some salient existing old node that has the value time, date time spec. In this case, the node after now. The revise operator non-destructively splices in this new subcomputation and returns a revised version of the most salient computation containing old. In this case, the subgraph for the previous utterance rooted at day of week. Okay, so we have this structure right here that is our existing dialogue information data flow tree. It's not a tree thing. So we have this structure and we're going to ask additional information about it. So we're going to look for a date time specification. And there's one here now. And then we're going to update the year. Oh, so it's got to be the old location has to be a date time specification. And then the root role constraint has to be an output. A revised version of the most salient computation containing the old, so the one that had now. In this case, the subgraph for the previous reference utterance rooted at day of week. So this is the bottom. I know that these were all represented going left to right, but I tend to think of graphs as going up and down, which is why I am confusing myself. So we have a computation that we had done previously, and we're going to do that exact same computation. We're just replacing. We're not replacing. We are adding a new piece of information here. Okay, so that makes sense. As in the refer example, the target program, though not the above subgraph, corresponds closely to the user's new utterance, making it easy to predict. Like the utterance itself, the program does not specify the revised subgraph in full, but describes how to find and reuse relevant structures from the previous data flow graph. So this revision doesn't say the whole path that you need to get through. It just says these are the things that the new path needs to have. Make sense? Given a data set of terms expressed in terms of appropriate graph manipulation programs, the learning problem for a Dataflow agent is the same as for any other supervised contextual semantic parser. We want to learn a function that maps user utterances to particular programs, a well-studied task for which standard models exist. Details of the model used for our experiments in this paper are provided in section 7. And then an aside on response generation. Okay, so I actually have a talk right after this, so I think I'm going to wrap this up here. I have a better idea what they're doing here. I also have a better idea what the revise does. So it adds new information that needs to flow through the same structure. And the specific things that this system can handle really well are very highly contextual conversations where there are a lot of references to things referred to previously, which I think makes a lot of sense for task-oriented dialogue, because you're often going to be like, hey, I need to change my account. The current number is 1234. Where the current number needs to refer to the account number of the account that I want to change. Yeah, interesting. I think my main confusion in this paper is, again, I have like a strong up-down bias, specifically for parsing, and it is not going up-down. And there's no reason it needs to. It's just that's my background. All right. So let's wrap it up here. We will jump back in next week, continuing with the same paper. I think there's a lot to unpack here, and it's definitely a very different approach than certainly what we're doing, and I think what the majority of dialogue systems are doing today. So I am, yeah, really interested to read more and look at some system evaluations and how training works and it works in practice. So I'll see you next week at the same time on Thursday for the paper reading group, and then tomorrow for live coding. Again, same time, we're going to be continuing to work on just making the, we have like a quiz bot, so taking the quiz and like changing the subject in the middle of taking the quiz and then going back to taking the quiz a little bit more seamless. So that's what we'll be working on. All right, thanks for joining today. A little bit of a shorter one, but I will see you all tomorrow for live coding, and then next Thursday to